Thanks, Kate, for the introduction. So for those not familiar with that castle, it's the most famous castle in Germany. It's Neuschwanstein Castle, built by the Bavarian King Ludwig II. The photograph is actually a historic one, which was black and white and got colored afterwards. So the only thing I added was the flag on top. Here is the tour plan. So that's the places we are going to visit in that castle. We are here. Can you see my cursor?
Move it around, wiggle it.
No, obviously you can't see it. So
yeah.
So we start at the left at the staircase. So just for general procedure, feel free to ask questions anytime. You don't have to spare your questions up to the end. I can handle questions in between. So we start at the left at the staircase and go into the Rotunda Scheduler, walk over to the Labyrinthum into Ferencia, to Fundamentum and Cella, and to the Laboratorium Magicum. So then we go back to the Rotunda. So that's going to be the tour of today. Enjoy. So scheduler is actually a real Latin word. It's not a made-up Latin word. It means it's a piece of paper or a plate where you can take notes on. But so it developed into what we call schedule today. The word. So this is really a Latin word, and it's the centerpiece of the OS. It's the centerpiece of the castle, but it's also the nicest place. Why? I explain that in a minute. And it has these niches around, which are, each of them is a wonderful place to look at. So let's go there and start. So in the middle, in the core, here we have the central scheduling decision function. What does it do? It picks the most eligible task to run on a CPU. Whatever that means, eligible. So most people associate that to priority, but that's not longer true. The invocation to go there is either voluntary or involuntary. So what does that mean? So voluntary invocation is if a task says, hey, I want to wait for an event, or I have to wait for a resource to become available. Wait for an event, you can say, I want to sleep for a specified amount of time and then be woken up again. Or I wait for a data packet to arrive over the network, or whatever it is. Waiting for a resource means either the task waits to get a concurrency control locked in order to access a shared resource, which might be shared memory or something like that, or it actually has to wait for memory to become available in memory allocation cases and things like that. So this is voluntary. It says, hey, I want to do this, and I know that I'm going to wait. So involuntary is when a task gets preempted because a more eligible task is available for that CPU. In the non-RT scheduling classes, or in the round-robin scheduling with time limits, or same applies to deadline scheduling with budgets. So the time slice of the task is exhausted, which makes the scheduler decides this task is no longer the most important thing to run. We take it away and give others the chance to run on the CPU. So here we have the four, or actually 3 and a kernel internal scheduling class. Early deadline first, that's the policies get deadline as seen from user space. We have the POSIX real-time scheduling class, which is the policies SCAD RR and SCAD FIFO, which is round robin and first in, first out. And then we have this completely fair scheduler with its scheduling subclasses or policies, SCAD other, SCAD batch, SCAD idle. So we don't talk about those in detail because they are not that interesting right now. Idle is an internal kernel internal scheduling clause, which is just there for ease of implementation. So the idle task becomes not something special. It's just the least important scheduling clause in the system, and it only has one task inside, which is the idle task, which is always runnable. So, and here you can see the scheduling decision order. When schedule is invoked, the scheduler just looks at the scheduling classes involved in that order: EDF, RT, CFS, and idle, and wherever a runnable task is available, it picks it out and breaks out of that decision function. There are a couple of more complicated things with nested scheduling groups, with C groups, but that's not really interesting in terms of what we want to discuss today. So, but this is very nice. It just works, and there's actually no need for Preempt RT to do anything about that. So we're done. We just have a real-time operating system, right? Yeah, that would be nice. I was hoping for that to be true, but that's not true. So we have something else in the scheduler which is important. It's Smp Load Balancing. It distributes runnable tasks around CPUs so that it ensures CPU utilization, so that we really can use the full Smp system, which is relevant for performance, for latencies, and for power management. We have quite some balancing points idle. At idle, when a CPU goes idle, it can look whether other CPUs have runnable tasks which it can get from there. On task activation, if a new task comes in, which is more important than the currently running task, it might ask whether some other CPU can take it over, or on task deactivation, it can look whether some other CPU has something more important to do. So it has push and pull mechanisms. That's the only place in the scheduler where we have to look at from the RT perspective, because there are a couple of decision functions there which might have quite a long runtime. So we have to either tweak knobs or disable some of the functionality. But it's not a complex undertaking. It's a constant source of trouble because the load balancing and the scheduler people change load balancing all the time in order to get more out of the systems, which trouble, but that's usually easy to fix and immediately visible. So, and as I said, we could be done now, but we are not, because a non-real-time enhanced Linux kernel has a large collection of interference sources, exceptions, interrupts, soft interrupts, interrupt disabling, preemption disabling, concurrency controls, resource allocation, and so on and so on. There's a lot of nasty things which can make Linux pretty unpredictable and pretty non-deterministic. So let's look at the different issues here. So the first thing when we look at it from the next to the scheduler is preemption disable. It tells the scheduler, hey, even if there's a more important task to run, you can't preempt me, you can't take me off the CPU and let this task run. So as a side effect, the task cannot move to a different CPU at that point, and it also prevents the CPU hot unplug as a side effect, which is that's just an implementation detail. But it's not only an implementation detail, a lot of code relies on that fact, unfortunately. But the usage is, it's a lightweight concurrency control between tasks on the same CPU, because it's just a counter which gets incremented and decremented when preemption is re-enabled. One of the common patterns, usage patterns, is to protect access to per CPU variables. Per CPU variables are a concept in the Linux kernel where we keep information strictly on per CPU, so that we avoid global data being accessed from multiple CPUs at the same time, which causes a lot of cache line bouncing and a lot of latencies in the hardware. So what's the problem with preemption disable? There's a semantical problem. Preempt disable is just, hey, don't preempt me. But it doesn't have an explicit protection scope. So it's not specified, it just protects world or on the CPU. For those who have been familiar with Linux for quite some time, I might remember the good old days of Smp issues we had with the big kernel lock, which was similar in its semantical undefinedness, because nobody knew what the kernel lock was actually protecting. At least we knew it at the very beginning, but later on the meaning got completely lost. So what's the issue with for real time? There's no we have no bound latencies in this preempt disabled sections, or we have preempt disabled sections which can have unbound latency. It's also used under the hood by other mechanisms. I come to that later, why it's necessary. So interrupt disable is very similar to preemption disable. It just is a little bit more heavyweight. It also prevents interrupt delivery to the CPU. It's strictly per CPU as well. So other CPUs can handle interrupts at the point, but not the local CPU on which the task, which is disabling interrupt delivery, runs. So as a side effect, it implies preemption disable, with all the problems it Preemption Disable has. The usage is to protect against interrupts in critical sections. And similar to Preemption Disable, it has the same semantical issues, and it's also used by other mechanisms under the hood. So it's not, but in these other mechanisms, the advantage is that we have a protection scope, because that's usually used with locking. So exceptions. There are different classes of exceptions available in a CPU: debug exceptions, error catching exceptions, and fault handling. So debug exceptions are the simple ones because they are user or administrator controlled. So if you run your real-time task with GDB and set a breakpoint and run into that breakpoint, yeah, I mean, then you can't expect that your task is going to meet the deadline. So it's harmless. It's something the administrator or the user actually wants to do. And in case that some other non-real-time task is debugged or instrumented with these debug exceptions, it doesn't harm the real-time behavior, because once the breakpoint in a task is hit, the task schedules out and the CPU is free for other processing. So this is harmless. Error catching exceptions. Hardware malfunction is one of the heavy ones. Machine check exceptions on x86 and other similar features on other architectures. Those can be fatal. They must not be fatal. Some of them are informal, but they are not too much interference sources. And then software malfunction, division by zero, undefined opcodes, and whatever. So if your machine takes a fatal machine check, then the real time of your most important task is out of the window. Machine is dead, so nothing the operating system can do about it. Same for software malfunction. If your real-time task actually has a division by zero, it dies. So nothing the OS can do about it. So it's nothing, the error catching exceptions are nothing we worry about too much. And similar, except for the hardware malfunction, but if in software malfunction, if some other unrelated task hits a division by zero or undefined opcode exception, then this task dies, scheduled out, and it won't affect the real-time task running on the same CPU. Fault handling exceptions are a little bit different. They are mostly related to memory management, user space mapping. So if a memory address which user space tries to access is not available, then is not mapped into the user space page tables, then it hits a fault exception. And depending on the fault type, minor or major, the impact can be significant. Minor faults are when the memory which is needs to be accessed is already available, and just the page table entry is missing. That's usually a quick exception which doesn't do much harm. Major exceptions are more problematic because the memory has to be allocated, or data like the application code or library code has to be paged in from disk or over network or wherever your storage is. So that can take quite some time and is unbounded latency. So in user space, this can be mitigated by careful application design and the setup of real-time applications can make sure that the stack is populated, that memory is locked into and paged in before the application actually starts running. So this is something which is purely a user space problem. It's not nothing kernel can do much about it. It provides the interfaces already. There's nothing new. What we need in real time, it's all there. The same applies for virtualization, but it's a little bit harder to mitigate. So there's more careful management of setup necessary than with regular user space applications. Interrupts. Those are nasty. Interrupts, when an interrupt hits the CPU, then the current execution context is interrupted. It interrupts or disabled as a consequence, and you can, during the handling of the interrupt, the scheduler cannot change context. It cannot schedule anything out. It has to wait until the processing has completed. We have basically two types of interrupts we talk about. Interprocessor interrupts, which is where which are managed by the operating system. So that's where which the OS needs on an SMP system to communicate between CPUs. They have various functionality, like just telling the other CPU to take care of something, which are quick and short interrupts. So something like rescheduling interrupts, which are related to load balancing or to device to task wake up when the task is placed on a remote CPU. But it also can run functions in interrupt context on a remote CPU, which is more expensive and can actually cause latencies and other problems. Device interrupts, depending on how well written the device driver is, many of the it's usually very quick, but quite some drivers do a lot of interesting stuff in interrupt handler context, and so they can introduce unbound latencies. But they have other problems. We come to that later.
Quick question, Thomas, since you said
yes.
So the device drivers, are there specific cases of things that they should be doing or should be avoiding doing, or is that going to be coming up later?
That's a hard to answer question.
Sorry.
You have no. I try to explain it. So so there's the real nice ones where RT does not care about is the interrupt comes in and just does a wake up of something, which is quick and it goes out and it's done. Then we have the others which have to do a little bit more interaction with the device, and often enough those require to take locks in that context. I come to the lock problem in a minute. And then we have the badly written ones, which do lots of processing in hard interrupt context, which is not only an RT problem, which is actually frowned upon in mainline in the non-RT scenario as well. But we have them and we have to deal with them, and we can't rewrite all of them. So the more recent drivers are usually people look at, or maintainers take care that for a general measure, the operations in the interrupt handler is not really expensive and long running, because people care about latencies on non-real-time system and responsiveness on non-real-time systems as well, and those would be in the way. So that's a general design consensus by now, but it still doesn't solve other problems, which I come to in a minute. So we have soft interrupts, which is a concept Linux has forever, I think. Well, not ever, but very early on. So what it does, interrupts raise a soft interrupt, and normally when the interrupt handler returns and the soft interrupt is pending, then it's handled on the return from interrupts, but with interrupts enabled, so it doesn't keep interrupts enabled. And then if there's too much of those things to process in soft IRQ context, then this functionality on a non-RT kernel wakes up a dedicated kernel thread, which then takes over processing of the soft interrupt under scheduler control. But soft interrupt processing also implicitly disables preemption, and soft interrupt disable, which is necessary to prevent soft interrupt processing from happening, disables preemption as well. So again, we have a source of unbound latencies there. So the next source of problems or concurrency controls. We have two main flavors, blocking locks and spinning locks. So the blocking locks and spinning locks, what's the difference? Blocking lock, as the name says, if the concurrency control cannot be acquired, then the task goes to sleep and waits for it and gets woken up when the other task which holds the lock releases it. Spinning locks is typically SMP concurrency control, because what it assumes is that, and it's a fundamental property of spinning locks, that the owner of the lock has to run on a different CPU. So basically, it spin waits until the lock becomes available, so it's not going to sleep. So this can be used in any context. So let's talk about blocking locks. So what do we have? Counting semaphores, redivider semaphores, per CPU redivider semaphores, mutexes, wait-bound mutexes, and the RT mutex. And the only blocking lock which actually is unproblematic for an RT kernel is the RT mutex, because it has priority inheritance or deadline inheritance built in, which prevents priority inversion, which can happen with any other of the blocking lock types, which again can cause unbound latencies. So spin locks. We have two types, spin locks, which are just one owner and n waiters. Reader-writer locks are different, so you have a single writer, and but you can have multiple readers in parallel. This is mostly used for things where something is rarely updated, but very frequently read. So you let readers on different CPUs in parallel access the protected resource, and only if an update is necessary, then the writer has to lock write, to write lock it, which basically locks out all readers, and they have to wait until the update is complete so that the data is consistent. Spin locks also implicitly have to disable preemption. Why? Assume you have a task running on a CPU, it takes a spin lock. Now it gets preempted, and the newly running task wants to acquire the same spin lock. It would spin forever because the lock owner is not longer running on the CPU and cannot release it. Also, we have locks which are taken both in task context and soft interrupt context, or task and hard interrupt context. So they have to either disable soft interrupt processing or hardware interrupts, which otherwise we would end up with the same problem of immediate deadlocks or live locks, because the lock owner would be interrupted, and then the waiter or the hardware interrupt context would wait forever and spin forever. But again, as we discussed before with preemption and interrupt disable or soft interrupt disable, this can cause unbound latencies, which is not nice. So the last major headache is resource allocation. So as I said before, if we have memory allocations, they can cause unbound latencies because the system might be under memory pressure, has to free up memory, drain caches, or swap out memory or whatever. And as I said, user space has mechanisms provided by the kernel to mitigate that by pre-allocating and locking memory. But kernel side allocations in latency sensitive or even in atomic regions are problematic for RT and require code changes in the kernel. So we have done quite some work on that already. There's a little bit left, or it keeps coming every now and then, but it's trivial to find usually, and hopefully it's trivial to fix in most cases. So let's walk to the fundamentum at Stellar. The fundamentum, the foundation, that's the low-level entry code, low-level exception handling and interrupt handling, and CPU and memory management. Most of those things are not problematic at all. So there have been issues in the past, but this got sorted, and so currently most people working on these kind of areas are well aware about the implications and try to do the right thing there. What we have, the horror cabinets in the cellar. One is badly designed code, so we cleaned up quite some of that. We have something what happens over and over again, layering violations where people try to be smart because C does not prevent them to fiddle in a data structure which should be opaque to the user, and they do their own tricks in order to spare 3 CPU cycles. Performance optimizations belong into the horror cabinet as well, at least partly, because quite some of them often try to do shortcuts through layers or violate willfully certain semantic constraints, which works or kind of works on vanilla kernels, but with RT it usually falls flat on the nose. So this is often enough. The layering violations and the performance optimization shortcuts, they are usually not that horrible to tackle. Badly designed code is what really takes time to sort out. So with that, we go to that laboratory where the mechanisms have been dreamed up magically, which we saw in the previous rooms. And the laboratory has obviously the same layout as the labyrinth. Let's start with the trivial, or maybe not so trivial mitigations, which are obvious if you think about it. We force hard interrupt handling into thread context, so it becomes scheduler controlled. We do the same with soft interrupt. And we enhance blocking lock mechanisms, which can lead to priority inversions with support for priority or deadline inheritance. Easy one, or not. So enforced interrupt threading, that's the infrastructure for that is readily available in the mainline kernel already. It's trivial for device interrupts, but it's not applicable for interprocessor interrupts and the CPU timer interrupts. So there's limitation to what it can solve. So let's just look at enforced interrupt threading of device interrupts. It's really only the first step for solving the problem. So because we have to preserve the semantics and we have to disable soft interrupt processing while the forced threaded handler runs. So, and as soft interrupt disabling requires preemption disable, we only have solved a very, very small part of the problem by that. So IPIs and the per CPU timer interrupt, they need deep inspection. There are possible ways to solve that. So we really have to audit the code passes. And one of the issues with the per CPU timer interrupt was POSIX CPU timer handling, not the actual runtime checks. They are quick and trivial, but what's expensive or impossible to do from that context on a RT kernel is sending signals to the process. So that got solved by splitting out that functionality and basically deferring it to task context and let the task kill itself once it tries to return to user space. So that's not only an improvement for RT, it's generally a nice thing to have for non-RT as well, because it makes the timer interrupt shorter. It puts the burden of signal sending, signal handling on the task which actually has the timer armed, which is good because the CPU time gets accounted to that task. We can make that code section fully preemptible on RT later on. And so these are the kind of nice ones. So, but for interprocessor interrupts, especially those which run arbitrary functions, we have to go and look at actually what the function does, what kind of work it does. Is it taking any logs which can be taken in that context on RT? And we have to implement the required functionality differently. So that's a lot of work. A lot of it has been done. We have there are several solutions to do that. Delegated to some other mechanisms like work queues, or implemented in a different way, so it can be done from a remote CPU and not necessarily requires an IPI to do that. So it really depends on the use case. You have to go through every single one and look at it and analyze it, whether it needs special care for RT or not. Often enough for those things, it turns out that solving it for RT is actually beneficial for non-RT as well, which is nice because that's the easy patches to sell to the community. That's the easy patches to get into the mainline kernel. So enforced soft interrupt threading. It's the logical consequence of forced interrupt threading. So we just do not allow soft IRQ processing on return from a hard interrupt handler. We just always delegate it to thread context. But again, this does not solve the problem that soft interrupt processing disables preemption. There's another side effect which is interesting. If we force all soft interrupt processing into the soft IRQ daemon thread context, that can have performance impact for non-real-time workloads. It depends on the workload you have. It depends on the scenario. So there's no, we can't make a general decision about that, but we had reports where this really matters. So this kind of workloads have to be looked at and then checked whether we can do something else for that, or whether we just have to live with the trade-off on RT. But that's for the point where we actually have a fully preemptible kernel. So enhance blocking logs with priority inheritance. So the approach we take for that is we take the existing or real-time mutex implementation and just make wrappers around it, which provide the same interfaces through to the kernel users, and preserve the semantics of these locking primitives for the users. But under the hood, they have an RT mutex which prevents priority inversions. And so that's trivial and straightforward for a mutex, because a mutex has basically the same semantics as RT mutexes. Mutexes are strictly single owner, and the owner has to unlock. The locker has to unlock. So nothing else can unlock these than the owner. All other blocking lock variants are not that trivial. So we look at them. We look at them later. Counting semaphores. Counting semaphores was the first blocking lock primitive in the Linux kernel. Counting semaphores are nasty because they have no strict owner semantics. They have so task A can lock it, and it can be unlocked by another task. It can even be unlocked in interrupt context or whatever. So there is no way to support priority or deadline inheritance with those locks, because you don't know what which entity should inherit the priority or the deadline if it's unclear, if there's no owner. So we cannot say which task is owning that and which task should run now in order to get out of the way. So fortunately, most of the usages historically, it's only in really, really old drivers, and everything else which was basically built around counting semaphores long ago has been replaced by a real proper semantically well-defined locking constructs. So we leave them unmodified. I haven't seen a report with this counting semaphore issues on RT for the last 10 years, I think. Early on, when we started, there were quite a few leftovers, but they are all gone. It's not an issue anymore, and it's just in bit rotting drivers who probably nobody cares about running on contemporary hardware. Reader-writer semaphores, interesting. Reader-writer semaphores, as I said before, with reader-writer locks, you can have multiple readers at the same time, and you can have only one writer. So if we do full priority or deadline inheritance support, that would require, if the writer locks it, that it basically inherits its priority or deadline to multiple readers, which has been tried. It was kind of working, but never really completely, and it would. We ripped it out before the deadline scheduler arrived, because then it would have been broken completely. So priority is only supported, inheritance is only supported when the semaphore is write locked. That means any reader which comes in to wait for the writer to go away can inherit its priority or its deadline to that writer and move it out of the way. That has a implication that if a writer has to wait until all readers left the critical section, it becomes writer unfair, which has been a problem in the original reader-writer semaphore implementation in Linux years ago, because some of the reader-writer semaphores are in interesting code passes where people observed writer starvation, because too many readers were constantly coming in and not letting the writer make progress. This has been solved in the non-RT implementation. We have strict writer fairness there, but with RT, with the priority inheritance or deadline inheritance mechanisms built around RT mutex, we can't do that. So it becomes unfair again, writer unfair. But we figured out that the workloads which actually triggered the rider unfairness are not the typical real-time workload. So I haven't seen any complaints in that regard since we started that. So doing the multiple readers, we had a single rider, which is basically converting the reader-writer semaphore into a mutex implementation in the early days, but that sucked too much. That was really creating trouble. So we went for the rider unfair solution, which works reasonably well.
Thomas,
And
is it okay to ask a couple of questions here?
Sure.
Do IPI paths include potential firmware entries that you are concerned about?
Pardon?
Interprocessor interrupt paths that include potential firmware entry that you're concerned about, or is that not a concern at all?
I'm not understanding the question. Where would be the concern?
If for any reason, if IPI involves getting into firmware path, like ACPI.
I mean, if you end up in firmware in a hot path, then your system is toast anyway. I mean, in terms of real time. So there's nothing the kernel can do about it and RT can do about it. That has to be analyzed on a per system basis when you do a validation for your system. So nothing. I mean, the entering firmware is very explicit on a couple of occasions. It's mostly during the boot process, and then there are a couple of other things where we write to persistent memory or things like that, or explicit EV access from user space. So I don't know. No, I don't think it's a problem here because that's none of the code passes will end up there.
Okay, similar to the MCI machine check you were pointing out earlier on one of the slides. Okay.
I mean, yeah. I mean, but if your user space initiates a EFI routine, which ends up calling into the firmware and then gets stuck in the firmware for a while, yes,
right.
Bad luck. That's like that. But that's a system design problem.
Right.
So there's
something system integrators or somebody that's evaluating their workloads and products for RT should be concerned about, but nothing kernel can do. That's kind of what I'm
no.
Right.
Right. If you configure your kernel to allow unrestricted access to EFI, and then some user space initiates EFI function which transitions into the firmware, yeah, what should the kernel do about it?
Mm-hmm.
The configuration allows it, so no problem. I mean that's the same. You can allow root to do nasty things, and so as long as the kernel doesn't care, it provides mechanisms for root to shoot yourself in the foot, and if you want to do that, please go ahead. So the kernel provides.
Oh, right. Go
The kernel provides mechanism, but does not impose strict policies.
Right.
Policy is mostly has to be solved in user space.
Thank you.
By restrict.
Right. I just I knew that would be the answer. I just wanted you to kind of say that for the benefit of the rest of the people listening, so that we are aware of that. Hey, you put RT kernel and we're all set. That's not really, and you have to look at the entire system,
Right.
and then the workload itself to analyze. Along the same lines, I found like when you were talking about the counting semaphores, being problematic, and I found 400 usages of up in the kernel, and a large number of them are coming from EFI as well. So something that kind of goes back into what you're talking about. If somebody allows user workload does EFI type access, and then you also have the up usage in that particular area.
Yeah, I have to look why EFI is actually using counting semaphores.
Mhm.
But because that's a relatively new user and it shouldn't do that. So that's a different thing what needs to be fixed. But even if you have a priority inheritance mutex there, it doesn't help if the mutex is held and the functionality vanishes into firmware for a while. So nothing the kernel can do about, because once you transitioned into firmware, the kernel is out of the picture.
Right. And some of these usages I'm seeing, they span wireless and then Ethernet drivers and then even DRM. So something, I guess,
Yes, some of the use cases there are actually really harmless. So some of the counting, there are actually reasonable reasons to use counting semaphores for some scenarios, but it's not. So if you look at some of the users in DRM, they are not in a code path which any real-time task ever should hit.
Okay. Any areas that concern you? Any usages that concern you in this respect? Counting semaphore usages, existing usages in the kernel.
I mean, we had counting semaphores basically all over the place, but most of them got replaced by either by mutexes or reader writer semaphores, or a mutex and a completion, depending on what the usage pattern was. So, but the remaining ones, I haven't looked in a while, but I haven't seen any complaints from people running into large latencies due to counting semaphores in the past 5 years.
Okay, thank you.
Welcome. So per CPU reader writer semaphores, there's no PI support possible because that's just not working in the way how they are designed. So the usage there is not really real-time sensitive. One of the main users is the CPU hot plug locking. So, but if you really want to CPU hot plug or take offline a CPU while your real-time workload is running, you probably have other problems than the CPU hot plug lock. It's not relevant. So because CPU hot plug is a latency source by itself, so that introduces latencies in quite big a way, depending on what hardware we are talking about and what kind of resources have to be torn down and things like that. So that's nothing I'm worried about. So it's a system design, again, a system design and a system policy decision. And if root decides to hot unplug a CPU while the real-time workload is running, I can't help it. Weight-bound mutexes. They are non-deterministic by design. So we had an attempt to do at least partial PI support, but it does not really make sense from the semantic aspect of weight-bound mutexes. So the main usage is in graphics drivers, and it's used in code passes where it's really, really hard to get locking straight, because some of the lock requirements come from user space, and we can't control what they are doing. So the weight-bound mutex is a way to do deadlock prevention on purpose under the assumption that either one side wins or the other, and the other which loses has to back out. So there is no semantically correct way to do priority inheritance here. But again, if your real-time application really wants to do real-time graphics on the screen, no, I'm not worried about that. It doesn't make sense. So you can do the computation for it, but in a real-time thread. But then you should actually move over the actual graphic output to something else, and that shouldn't be real-time sensitive. So the next level of mitigations we come to are the spinning locks. What can we do about them? So spin locks, as we have spin locks in low-level management code, like direct hardware management, or in the scheduler, where we can't, where we have to preserve the existing semantics, where we have to keep interrupt or preemption disabled. But most of those places are well-defined and have bound latencies, and are usually not a matter of concern, so that the preemption or interrupt disabled regions are rather short, and we have to have them because we can't allow concurrency here for obvious reasons. I mean, it would be funny to think about scheduling in the scheduler. Might be something interesting for academics, but I'm not too interested in figuring it out. So, but in most other areas, they can be substituted by something else under a few assumptions we make. Reader-writer locks, there's no usage in low-level management code. There was early on, but we fixed that and it went away, thankfully. So what we have to think about is, when we talk about replacing spin locks with something else which can do priority inheritance and therefore has to be able to sleep, then we have a few constraints which we need to get out of the way. One is we have to full thread interrupt handlers. We have to, and of course, soft interrupts. We have to forbid that these kind of sleeping or substituted spin locks are taken in hard interrupt context. And we have to make sure that they are not taken in atomic contexts like preemption disabled or interrupt disabled context, which excludes scheduling or the ability to schedule. So what we did, and that has been done long ago, we split spin locks into two types, a raw spin lock and spin lock. The raw spin lock is preserving the spinning, preempt disabling, and eventually interrupt disabling semantics, and it's used in the core scheduler. It's used in a few other places like timers. It's used in low-level hardware management routines where we have short, well-defined, bound lock-held regions. most of these conversions have been done already and are part of the mainline kernel. So developers are aware of it, that they usually should use spin locks and not the raw ones, and have to actually make an argument why they want to use a raw one. And we have the regular spin lock, which can be used basically everywhere else. It's mapped to raw spin lock for non-real-time kernels, so it has the same semantics as it had before. And on RT kernels, we have a wrapper around RT mutex, which uses the RT mutex internals for priority or deadline inheritance. So, but this has a twist. If you look at blocking locks are always called in a state, in a task state where the task state is running, which means the task can just go to sleep, set the task state to something else when the lock is contended, schedule something else, does the unlock, wakes it up, and the result is task state is running. Fine, works great. With spinning locks, we can have a task state which is not running. A lot of spin locks are taken in preparation for going to wait for I/O completion or waiting for some other event to complete. So the task sets its state to interruptible or non-interruptible and whatever. So in the non-contended state, we just go out and nothing changes. But in the contended state, we have to change the task state to something else, schedule, and then we have an unlock and a wake up, and unconditionally, the task state is running. So if we get there, we basically have a different task state than as we entered the locking function, which is wrong. We cannot do that. Because then the following code, which actually depends on the state being not running, will do the wrong thing. So on the left side here is part of the solution is if we run into that situation, we say, okay, we have a separate storage in the task where we just save the state which we have when entering the lock section. Then we have a state which is explicit. Hey, we are waiting for a lock. We schedule, we get the unlock, wake up, task. After that unlock, the wake up or T-lock happened, the task state is running. But before we go back and proceed, we restore the saved state. Sounds good. Is it complete? Unfortunately not. So because, as I said, if the task state is not running, then the task usually queues itself for an event to happen or something to complete. So there's yet another wake up which is involved in that scenario. So let's look at it again. So we said, okay, we save the task state, we set it to wait for the RT lock, schedule out. Now comes the unlock and the wake up RT lock, which makes it running. And then we have restored the task state at entry. But if the event which wakes it up happens at the same, in that blocked section where we're waiting for the lock, then the task state of the task should be running when we leave, which is not, because we just restored when we had entered. So here is the full solution to that. If we run into that situation that the event wake up, which brings the task out of the non-running state again, happens while the task is blocked on the lock, then it doesn't operate on task state, it operates on the saved state. So once we get out of schedule because the wake up of the RT lock happens, we restore the saved state. And no matter what, when we have a no wake up, then we restore the saved state as we entered. And if we have that event wake up, it's going to be running. So it's under all circumstances correct. Once you know how that works, it's simple, right? Took us a while to understand it. So, but now we have preemptible spin locks. Great, hooray. But here comes the next issue. Once it is preemptible, the scheduler can migrate a task to a different CPU, which is fail. Because spin lock sections guarantee that a task cannot migrate, which is required for CPU data correctness, because the semantic properties of spin locks in the non-real-time kernel guarantee that, and we have to guarantee that as well on RT. So the solution for this was to prevent or disable migration to a different CPUs for spin lock held sections. It was the obvious solution, but it wasn't that popular because migration disable has an impact on schedulability because the scheduler cannot decide to move the task around. And as I learned, it's not well studied in scheduling theory, but at some point they had to bite the bullet and actually get it upstream. It's useful for other purposes. We have the K-map atomic, the K-map local conversion, which is already upstream, which helps upstream as well, which relies on migration disable. And we have a couple of other RT mechanisms, smaller ones, where we need the migrate disable mechanism to work. Reader-writer locks. Thankfully, we didn't have to split them into raw reader-writer locks and reader-writer locks. Wouldn't be that hard, but sparing yet another split is a good thing. As discussed with reader-writer semaphores, we can do full priority or deadline inheritance support because, again, this would require to do multi-reader inheritance, which is not possible. And even if it might be possible, it's probably horrible. So we only have TI when it's write locked. Same as for reader-writer semaphores, it becomes writer unfair. We have no writer starvation observed so far, as many of the critical use cases where this was problematic before have been replaced with RCU-based solutions in mainline. So we are not that concerned about the remaining users, which are in a few places, but it's not that a widespread problem as it used to be. So we have more magic mitigations coming. We have to make soft interrupt preemptible. So soft interrupt disabling happens in the non-RT kernel just as part of the preempt counter, because it implicitly also disables preemption. It's easy, it's just one part of the preempt count. So we have to split that out, separate that out. And we use a per CPU lock, a sleeping spin lock, which has recursion support, because we have nested local bottom half disable sections. So we have to handle that. And of course, we have the same issue as we have with spin locks. We have to disable migration inside of these sections. But we have the migrate disable, so it's not that horrible. There's quite a challenge there to handle early boot correctly, where we have interrupts or preemption disabled and basically cannot do the full substitution. We have mechanisms to handle that. It's not pretty, but it works. So with threaded interrupt preemption, we run the interrupts with the interrupt handlers with interrupt enabled, and we have our lock-based soft interrupt serialization allows us to enable preemption. Also in the threaded, the force threaded interrupt handlers, at least those which can be force threaded. This, of course, requires the spin locks to be substituted, and that's where we have most of the things in place now. So we have a few remaining pain points where we need to look into. We have standalone usage of preempt and interrupt disable. So the vast majority of preempt and interrupt disable is indirect. It's coupled to locks, it's coupled to spin locks or reader writer locks, which is easy because we have that under control. We have explicit locking scope there. We have a protection scope, and not something which is, as I discussed before, semantically not really well defined in terms of protection scope. So we actually have to look at the usage size again. So we have the low-level management code for hardware, scheduler, and other things where we have a valid usage, where we have a required usage, so we just leave them alone. We have small, well-defined critical sections and well-confined critical sections where it doesn't matter, where the protection scope is clear, where there is no real impact because it just protects a couple of instructions and then it's done. There's no point in actually thinking about converting that to anything more complex, because that would be a performance issue and a lot of overhead for no value. We have open-coded interrupt disable and spin lock instances where people will try to be smart. So those can be converted into regular spin lock IRQ save and spin lock IRQ restore, or spin lock IRQ and spin unlock IRQ code constructs. That's usually not problematic, but there are a couple of things where we really have to think about what to do about standalone preempt or interrupt disable regions. So here we came up with a concept which is named local locks. Local locks are strict per CPU locks, so you can take them across CPUs. That's not possible, or it would be possible, but it's not exposed in the ABI, no, in the API. So one of the nice things of local locks is we can define a protection scope for these regions. So on a non-RT kernel, this local lock functions just map internally to preempt and interrupt disable. And what we gained with that, and that was one of the main selling points upstream, was it provides locked-up coverage, even on non-RT kernels. So because now the lock has a scope, it can be tracked by, or the protected section has a scope, it can be tracked by locked-up. And we actually, when we did that early on in the RT kernel, before we brought it upstream, we actually found bugs that way. And the local lock is really nice because on RT we just make it under the hood look different and use a per CPU spin lock, the sleeping variant, the substituted variant, and so we have a full protection, which works on RT and gets rid of the interrupt or preemption disable problems. So we have spin lock nesting issues. These substituted sleeping spin locks can end up in preemption interrupt disable sections. So we have to look at it and think about solutions, reworking the code, because some of them really need to be converted to raw spin locks because they protect low-level hardware or low-level functionality. And we came up with mechanisms like simple ways to squash full classes of problems. There's another nasty stuff is trilock and spin weight loops. Trilock loops are usually used to avoid lock order inversion. So if you have a code path, it takes lock A, two locks in A, B order, and you have another one which has to take it in B, A order, then the second one has to do lock B and trilock A, otherwise you can end up in a full deadlock. So how that works is it locks B, then it locks A. If it trilocks A, if it can't lock it, it goes back, releases B, and then starts over by locking B, trying again until you can spin. But this works if on a non-RT kernel, because there it's guaranteed that both entities run on different CPUs. But on RT, you can end up on the same, that the task which does the reverse and trilock dance preempts the task which actually holds lock A already, and then you live lock because task B, which does the trilock, might be higher priority, and it just keeps trilocking. Will never succeed, will never make progress. Spin locks, spin weight loops. There are other constructs in the kernel where actually we know that, or the non-RT kernel is guaranteed that the operation runs on a different CPU. So it can spin wait, busy wait for the operation to complete. It's slightly different from the trilock loops, but it's the same problem, because we can end up in the same scenario as with trilock loops, doing the spin wait on the same CPU as the actual preempted computation or critical section, and we will just wait and spin forever. So the solutions are only code rework. We had a couple of things which were really nasty to fix and hard to solve problems, or we had the easy ones where we came up with new mechanisms like the timer expiry lock, where we could squash a whole set of problems in one go. So this was a conceptual design where we said, okay, we can solve this differently by actually having something to block on, which is guaranteed not to lead to that live lock or deadlock situation. So, but all of these things need to be looked at very carefully. So now we have our magic laboratory filled with all these bits and pieces, which we discussed. And I have A, B to set various tweaks and tweaks, which we didn't discuss yet or can't discuss as a scope of that, because there's really small details which are not only for particular code passes and not interesting for the big picture, but they still have to be in place. So one of the challenges there is, as you noticed when I was talking about force threading interrupts and force threading software interrupts, we have multiple and circular dependencies of our mitigation mechanisms. So some of them just work when we can have everything in place. And the other challenge, which we really suffer a lot, and we still suffer from it, is unclear semantics in non-real-time kernels, because we have implicit protections, and we have unspecified protection scopes where we actually cannot figure out what's protected, which makes it hard to make a decision. So you have to really go and analyze large code passes in order to figure out whether there is an assumption somewhere that something protects something which is not documented or not clearly specified. So with that, we leave and go back to the rotunda, and with all these things in place and a couple of minor tweaks, the scheduler has now maximum control over the CPU, but be aware of the dragons. They are lurking, and every bit of new code, every driver you write or vendor code you get might have some of those issues, which we just went through and discussed. So that's pretty much the end of the tour, and I think we're running at the end of the time slot. So I have just one slide left before we go to questions. So that's the causal maintenance. So like a real causal, maintaining such a thing is not free, but funding of that is and always was a challenge. We currently have a funding gap which stalls development and maintenance, and we really have to close that gap to ensure mainline integration. If you can help, please contact Kate Stewart at the Linux Foundation. She's the maintenance fund manager.
Don't know. Do I put this on as my new title, Thomas?
Yes. So with that, we are at the end of the tour, and I'm open to questions.
So Thomas, I have one question. You went through a lot of gotchas in terms of for RT, being able to links to workloads, links to architecture, links to perhaps config options. Do you have one single slide that says, do not do this, or do it at your risk kind of slide?
No, not really. I mean, there are so many things you shouldn't do, but many of them are actually documented in the wiki or in other publications. So no, there is no slide here. Don't do this. I mean,
is that part of the kernel documentation at all?
No, there's some. So there's, for example, the whole locking, nesting, things which is important for people doing driver development or things like that, and want to figure out what lock constructs they can use. So this is documented. That's part of the kernel documentation. There's a large document which actually describes also the differences and why RT cares about certain lock constructs and what kind of open-coded sequences you should avoid. So that's part of the kernel documentation.
Thank you.
We also have a question from the chat is how many are working on RT?
Right now, nobody. As I said, we are stalled. So usually, for the last couple of years, we were basically a team of 5 people funded to work full-time on mainline integration and maintenance. And we have, aside of that, we have the people who are maintaining the stable kernels, which is mostly part-time, funded by their respective companies, or it's just volunteer-based. And then, of course, we have some of the companies who are involved in the RT funding project, who have their own RT teams for their productization of RT. Who have people who actually look at RT behavior, and we have a couple of people working on different aspects like validation or verification. So there's a wider community around it, but for the upstreaming effort, that was pretty much the funded team of 5 people doing the work so far. And a little bit help from here and there. So it's pretty much about that.
Another question from the chat is from Leonidas. Thank you for the tour. Are the changes you described upstreamed, or are they maintained out of tree in the RT patches?
So the part of the changes are upstreamed, but there's the real core changes are still out of tree. We have a plan to upstream it once the other problem is solved.
I have one more question, Thomas. You mentioned that part of the problem is like shoveling snow while it's snowing kind of situation, where you might have drivers and new code coming in that could violate some of the RT constructs and make trouble. So do we have any scanning techniques to find such code in terms of Kachi check or any other static analysis type tools?
I'm not sure that I'm not aware of any Cochinelle scripts. I think I have a few which I use. Sometimes I probably should upstream them at some point. But
those primarily static and dynamic analysis type ones? Sorry, yeah, upstreaming will be great.
It's static.
Okay.
The ones I have is basically static. The other stuff is, if you enable lock depth on an RT kernel, then we also have all the lock nesting checks enabled. So lock depth will yell at you immediately. So we have the runtime analysis is there. This is part the raw lock nesting issue is covered upstream already. You can turn it on a non-RT kernel, but it's noisy as hell because some of the problems we have still, where we have the fixes out of tree, will still make give you a lot of places which violate those assumptions right now. But that's something which really needs the full thing.
Thank you.
I'm seeing a comment in from Lucas